Okay, here we have our equation again, and what we want to do is figure out how spontaneity is affected by temperature change. So in our first example, and I think I'm going to just rewrite this right above so that we can see it a little bit better. So in this first example, we have an exothermic reaction, meaning we have a negative delta H value, and there's an increase in entropy, meaning my delta S is going to be a positive value. Well, what I'm doing is I'm saying a negative minus T times a positive, so plus this negative value. My temperature, whenever you have a negative plus a negative, that's, let's write that down, negative plus a negative, it's always going to be negative. So therefore, it is going to be spontaneous at all temperatures. So in order for this to work, remember, we want our delta G we want it to be negative for it to be spontaneous. So the way I did that again is I just took my negative for my exothermic, I subtracted my positive, which makes it be plus a negative when I change the sign on that. So again, negative plus negative is always negative. It would have to be spontaneous at all temperatures. Next one, I have an exothermic reaction. So again, we have a negative. But what we're going to do is we're now going to subtract our temperature times a decrease in entropy. So that's going to be a negative value over here. We're subtracting that. So in this case, remember we've got temperature right here. You're going to be saying that you're going to add, and you're going to switch the sign here as well. So you're going to add I'm trying to think of how we want to say this. If you're adding this, then that's going to be, if you have a negative plus a positive, and here's your temperature right here, then your temperature would need to be low for delta G to be negative. So in other words, for delta G to be spontaneous. The only way that would work is if this value here was a low temperature, so it ended up being more negative in your reaction. Next one, we see that we have an endothermic reaction, and in our endothermic reaction, that means you've got a positive value. You're subtracting your T, and it's an increase in entropy, so you're subtracting a negative value over here. If it's you're subtracting a positive value over here since it's a increase in entropy. So in this case, you would say you have a positive minus a positive. Well, if this T value is big, then you'd end up getting a negative value. If this is small, then it would end up being more positive. So in this case, we're going to say that temps need to be high for delta G to be negative. In other words, for delta G to be spontaneous. And then our last example, here we have an endothermic reaction, so we have a positive value here for our delta H. We're subtracting our T, and it's times a decrease in entropy, so this is going to be a negative value here. So in other words, we would say plus, plus, and it looks like it's always going to be positive. So positive plus positive is always positive. Therefore, it is never spontaneous at any temperature. Okay, here's just a table that kind of illustrates what we just talked about, so you can look at that for a little bit if you'd like. Okay, now next question. What is the situation that occurs when a reaction is neither spontaneous in the forward or reverse direction? Well, we talked about this when we talked about equilibrium, and that's what the term is. It's at equilibrium. when that's the case, when it's not spontaneous in the forward or the reverse direction. And what would our delta G value be? Well, it's not spontaneous in the forward direction, that would be a negative value, and it's not spontaneous in the reverse direction, which would be a positive value. Instead, it is just equal to 0. And our last question. At what temperature does the following reaction reach equilibrium? What is the physical significance of this temperature? So all we're seeing is that water goes from the liquid phase to the gas phase. I'm looking for temperature, so obviously I can't assume this is at 25 degrees Celsius, so I'm going to have to go ahead and use the formula of delta G equals delta H minus T delta S. And so I have to do the laborious process of going through and calculating my delta H values and my delta S values. Okay, so I used Big Mama and I tried to figure out my delta H, and I go through the math and I get 44.012 kilojoules. Do the same thing for my delta S, and when I calculate it I get 118.915. But it's in joules per Kelvin, so I need to make sure that I convert that, and it becomes 0.118915 kilojoules per Kelvin. So now that we have those values, we can go ahead and plug it in. And remember, we've already said that in this situation, we're talking about reaching equilibrium. So we know our delta G value. We're solving for our T in this situation. So we're going to say that our delta G is equal to 0. Our delta H is equal to 44.012. We are subtracting T times our delta S, so we're solving for T, and our delta S is 0.118915. So when we solve this, we get T equals 370.1 Kelvin. Well, let's put that into something that we're a little bit more familiar with, some units. So if you subtract your 273, you determine that that is 97.1 degrees Celsius. You know what, that's pretty darn close to 100 degrees Celsius. Our pressures might be off a little bit, but in this case we're going to say that this is it's roughly equal to 100 degrees Celsius, and that significance, hopefully you're figuring out, is the boiling point for water.